Hi, my physics students. Welcome to another fun video with Mr. Bozadeh. Today we're going to be looking at kind of the way that I go about solving a Newton's second law problem where you've got forces on an object and you're either solving for an unknown acceleration or maybe you're using a known acceleration to solve for an unknown force. This is kind of the thought process. I thought we'd start out by looking at a quick snapshot of the thought process that goes through my mind as I solve one of these problems. As always, you want to get some sort of visual representation with our free body diagram. So always start by drawing your free body diagram. The next thing you want to do is you want to set up our net force equations in the x and the y direction. We know that if the forces are unbalanced, then one's bigger than the other in like the x or y direction, then you're accelerating. And if you're accelerating, then we know our net force is going to equal mass times acceleration. If the forces are balanced, then that means you know that we're either going at a constant velocity or we're at rest. And that means that our net force is going to equal 0 newtons. Write out your forces symbolically with a plus or minus in front of them, depending if they point in the positive or negative direction, or positive or negative direction, vertically or horizontally. And then you want to solve for as many of your force values as possible using force equations that we already know. Like force gravity equals mass times the gravitational field strength, or maybe force friction equals mu times force normal, or you could just use trig functions if a force is at some sort of an angle. You may also need to use kinematics equations to get acceleration if you're given those values. Finally, you solve for your unknowns. All right, let's take a look at a problem. All right, here's an example of a Newton's second law type problem. In this problem, I am pulling my two kids on a sled, and we want to know if I'm pulling with a constant force that's accelerating my kids, how far will my kids travel in 4 seconds if all these things are given. So here are the things that were given. My kids and the sled have a mass of 80 kilograms combined. The string that I'm pulling makes an angle of 20 degrees to the horizontal. I pull with a force applied of 300 newtons. And the coefficient of kinetic friction between the sled and the snow is a value of 0.35. So those are all our givens, and let's make this go away and let's solve this problem. Okay, so first things first, we want to, as I said, draw our free body diagram. So I'm going to start by doing that. We've got this dot which represents my kids in the sled, and we know that I'm applying a force applied at an angle, like so. We know that we've got force gravity of the kids and the sled combined. We know that there's a friction force that is opposing the motion of my kids, and then we know that we've got a normal force like that. Let's list out those givens real quick. We know that the angle that I'm pulling at is 20 degrees. We know that I'm pulling with a force of 300 newtons. We know that the mass of the sled and my kids combined is 80 kilograms. We know that the kinetic coefficient of friction, or mu sub k, is 0.35. And as we've discussed before, there's no units on the kinetic coefficient of friction, or coefficients of friction in general. So let's see. Let's just talk about the free body diagram to start with. We know that we can think of that 300 newtons of applied force as being somewhat in the x direction. So there's an x component to my applied force, and there's a y component to my applied force. We know that in the x direction it's accelerating. The problem said that my kids are speeding up. So that means that the force of friction should be smaller than the applied force in the x direction. So I'm going to shorten that vector arrow to make that a little more clear that we're accelerating in the x direction. And we know in the y direction the sled's not accelerating up or down. It's a rest in the y direction. And so these forces in the y direction should all be balanced. So the normal force, the applied force, and force gravity should all be balanced. I'm going to make my normal force a touch smaller, like that. So it looks like these two are combined to equal that one. And that makes sense, because when you lift up on something, your normal force is going to end up smaller than force of gravity, because your upward applied force is helping to balance out force gravity. Great, so let's dive into the actual calculations now. As I said, the next thing you want to do is you want to set up your net force x and your net force y equations. So net force x right there, and we'll do net force y right here. As I said, if you are accelerating, then we know that net force equals mass times acceleration in that direction. If you're not, then your forces are balanced, so then the forces cancel out or balance out to equal 0. So in the x direction, we're accelerating, so we know net force x is going to equal mass times acceleration. In the y direction, we are not accelerating, so those forces are going to combine to equal 0 newtons or balance each other out. Let's list this out symbolically. In the x direction, we've got negative force friction, because it points to the left, plus force applied x equals mass times acceleration in the x direction. In the y direction, we've got plus the force normal, because that points upwards, plus force applied y, because that points upward, minus force gravity, and those things all balance each other out to equal 0 newtons. So now the next thing I mentioned that we want to do is we want to try and see how many of these values we can calculate, right? Off the bat, we don't actually have given any of those values. So, but we have ways to find a lot of those values. So let's dive in and see how many we can find. The first thing that comes to my mind is let's find the applied x and y direction components of that 300 newtons. So to find the x, we're going to use cosine of 20 degrees. So 300 newtons is our hypotenuse times cosine of 20 degrees is going to give us our applied force in the x direction. And I multiplied that out already, and that gives us 281.9. So 281.9 newtons is the applied force in the x direction. The hypotenuse, 300 newtons, times sine of 20 degrees is going to give us our applied force in the y direction, and that comes out to be 102.6 newtons. 102.6 newtons. So we know those two forces. We can also find force gravity. So let's see, force gravity we know is equal to mg. Our mass, the mass combined mass is 80 kilograms. We know that the gravitational field strength is 9.8 newtons per kilogram on Earth, so we can multiply those two together, and we find that the force of gravity is 784 newtons. So let's see, now we know these things. We know force gravity, 784. We know force applied x, which is 281.9. And we know force applied y, which is 102.6 newtons. Okay, so now we can come back and we can ask ourselves, all right, so in the y direction we've got one unknown, and in the x direction we've got one unknown. Actually, we have an equation for force friction. Let's go ahead and give that a shot and see what happens. So if I write out my force friction equation, it's force friction equals mu times force normal. What I'm going to discover is I've got the mu, I know that value, that is 0.35, but I don't know the normal force. That's unknown at this point. And don't make the classic mistake of plugging in your force gravity for the normal force every single time. Because as we've discussed, that's not always true. The normal force can change while your force gravity is always constant. The normal force could get bigger or smaller depending on other forces in the y direction and how they help to balance out the force of gravity. So it looks like we can't actually use our equation for force friction yet because we don't know the normal force. But what we can do is in the y direction, we know force gravity, we know force applied y, and we see that since they're all balanced, the only unknown is the normal force, so we can solve for that. If, on the other hand, we looked at our x direction, we'd find that we'd have two unknowns. We know force applied x, we know mass, but acceleration and force friction are both unknowns. So we'll dive into the y direction, and we'll say force normal plus force applied y, which is 102.6, minus force gravity, which is 784. Those combined equal 0 because they're balanced out. And when we add 784, subtract 102.6, we discover that our normal force is 681.4 newtons. So force normal comes out to be 681.4 newtons. There we go. So I will add that to my free body diagram. This is 681.4 newtons, like that. I guess clearly my free body diagram isn't as nicely to scale as I might have liked it to be. This should be longer, this should be shorter, but still they combine to equal force gravity. Well, now that we have the normal force, we can come back here and we can use that to find force friction. So coefficient of friction, the kinetic coefficient of friction is 0.35. Our normal force we now know is 681.4 newtons. multiply those together, and we discover that our friction force is 238.5 newtons. 238.5 newtons is our force of friction. Okay, now if we come back to our net force equation in the x direction, now we discover that we've got this value, so our only unknown is acceleration, and we can solve for that. So we go ahead and we plug in our numbers, negative 238.5 plus force applied in the x direction, which is 281.9, is going to equal mass, which is 80 kilograms, times acceleration. So we combine those two, that gives us, those add up to 43.4. So 43.4 newtons is going to equal 80 kilograms times our acceleration. Divide the 80 over, and we find that our acceleration is 0.54 meters per second is our acceleration right there. Now, if you think back to the original problem, we've essentially solved the Newton's second law portion of this problem, but it actually asked how far, what distance I pulled my kids in 4 seconds. So now we need to think about kinematics. Well, because we solved for acceleration, we're going to be able to use kinematics. For example, if we were to list out our variables, position initial, position final, initial velocity, final velocity, acceleration, and time, we know that we can say that they started initial position of 0 meters. We don't know how far they travel, that's what we're trying to find. They start with an initial velocity of 0 meters per second. We don't know what their final velocity is. We didn't originally know what the acceleration was, but we were asked how far they went in 4 seconds. Now that we know acceleration, 0.54 meters per second squared, now that we have that value, we can use our kinematics equations to solve for that final position. So we can say position final equals position initial plus initial velocity times time plus 1/2 acceleration times time squared. And since the initial position and the initial velocity are 0, those can both go away. So what we find is that the final position is equal to 1/2 times acceleration, which we know is 0.54 times the time, which is 4 seconds squared. And if you multiply that all together, you're going to discover that I pulled my kids a distance of, or displacement of, or over a position of 4.3 meters. So there you have it. That is the full problem. If I pull my kids with an applied force of 300 newtons at an angle of 20 degrees, where the kinetic friction coefficient is 0.35, and my kids in the sled have a mass of 80 kilograms, if I pull them for 4 seconds, they're going to accelerate at a constant acceleration of 0.54 meters per second squared, and they're going to travel 4.3 meters. I hope that was helpful to you.